So now we spent a fair bit of time looking at the solutions to the harmonic oscillator in general. The next thing we're going to do here is look at a couple of examples. But before we do even that, I just want to say a couple of words about energy in simple harmonic motion. That's what the motion of a harmonic oscillator is known as, simple harmonic motion. So if we look at the potential energy first of all, that is 1/2 kx squared. So we know, of course, that that is 1/2 k times x, which is a squared cosine squared of omega t minus delta. So that's the kinetic energy, potential energy. Kinetic energy is next. That's, of course, 1/2 mv dot mv squared, or 1/2 mx dot squared. Now, if you remember the formula we had for the velocity as a function of time, it's just a time derivative of this. It's going to be minus omega times this. Let's just do it. The velocity as a function of time is minus omega a sine of omega t minus delta. Okay, so we plug that in here, we get now we know that omega is the square root of k over m. So this means that m omega squared is equal to m times k over m, that is k. So the kinetic energy is therefore equal to okay. And now we can, to find the total energy, we just add the two together, as usual. And as we can see, they have a common factor of 1/2 ka squared. And this is a cosine squared plus a sine squared, that's 1. So this is just equal to 1/2 ka squared, just like we knew it should be. Right? We've only shown that the initial energy of an oscillator is this, if it started at the turning points. But it makes sense that the energy should be that value throughout its entire motion, because we're dealing with conservative forces here, obviously, because we're having a potential. And so we can see that there's no dependence on time. We do also see that the energy is proportional to the amplitude squared. So that's a general feature. If you double the amplitude of any oscillator, its energy actually goes up by a factor of 4. And that has to do with the square dependence here and here of the velocity and position in the energies. Okay, so that was the last bit of general information I wanted to give before going into a couple of examples. So the first example is that of a bottle that is submerged in water. So we have some weighty stuff here at the bottom of the bottle, and it's bobbing up and down in the liquid at a distance between the surface of the water and the middle of this heavy liquid we call D. Right? So if we now look at the forces that are acting on the bottle, we have a downwards force, which is the total mass of the whatever is down here times G, and upwards we have a buoyancy force. The buoyant force is due to the mass of the displaced water. The water has some density, rho, and the amount of volume that's being displaced is essentially the area of this bottle times its the amount it's submerged by, which is D. Doesn't look like that's what it is, but okay. So we have density rho. The force is therefore going to be the total mass of the displaced water. That is rho times the volume times G, and it's going to be in the upwards direction. So really, it's minus g, minus vector g there. The volume is the area times the distance, so this becomes rho a d times g in the minus g hat direction. Okay. Next step is, of course, to do Newton's second law. That is, so far, always our starting point. So the total force is just the sum of these two. If we pick the upwards direction as positive, then the force is a rho g d minus mg in the minus g hat direction. And this is going to now be equal to the second time derivative of position, right? So that's the total mass of the bottle, which is m, times d double dot, also in the minus g hat direction. So for that reason, we get the differential equation, if you just look at the components here, of a rho gd minus mg equals m d double dot. So this looks approximately like the differential equation for harmonic motion, but not quite. We have the second time derivative of a position, and then we have the position itself times some constant. But we also have this extra thing here, minus mg. That's because the equilibrium point is not at d equals 0. So to get away from that, we will redefine our variables a little bit. So if we are in equilibrium, we know that the net force is 0. So let's do that here. We're looking at equilibrium. F equals 0, and we're going to call the d at that point d0. So if f equals 0, that means that this has to be 0. Like that. And then we're going to define a new variable. We're going to make a change of variables. You'll see that d equals d naught plus x. So x is now the deviation from the equilibrium, and that moves, as far as x is concerned, the equilibrium back to the origin. So what do we get when we plug this in here? Well, first of all, if this is true, then d double dot is equal to x double dot. So if we then, as far as the right hand side here, things are pretty straightforward. On the left hand side, so we get mg minus mg. If you want to write it on the standard form, we divide by m. Actually, I just noticed here that I made a sign error. Over here, the force is this, but d is counted in the upwards direction. So we actually need, or in the downwards direction, so we actually need a minus sign here. So we get a minus sign everywhere here. So now this is almost the same as d naught. So we end up with x double dot equals minus g over d times x, which we could write, if we like, as minus omega squared times x, where omega is the square root of g over d. So that is now the equation of motion. And of course it has the usual solution. I have to scroll this off the screen here a little bit, the bottle, but hopefully you remember what it looked like. So we get the usual thing. X of t is equal to some amplitude times cosine of omega t minus delta. And omega is the square root of g over d. If you want to calculate the period, that's just 2 pi over omega. So that is 2 pi times the square root of d over g. So that is the solution to this problem. The next problem is going to deal with a potential that is not perfectly harmonic, and we're going to make an approximation for small excursions around the equilibrium. But it won't fit into this video, so we'll make a separate video for that example.